Hello, YouTube. Just thought I'd do a video on reading a book that I'm currently reading on the subject of consciousness, neuroscientific explanation, and evolutionary origins. Called Consciousness Demystified by Todd E. Feinberg and John M. Mallat, published by MIT Press, I think, yes. The abstract basically says, consciousness is often considered a mystery. How can the seemingly immaterial experience of consciousness be explained by the material neurons of the brain? There seems to be an unbridgeable gap between understanding the brain as an objectively observed biological organ and accounting for the subjective experiences that come from the brain and life processes. In this book, Feinberg and Mallat attempt to demystify consciousness, to naturalize it, by explaining that the subjective experiencing aspects of consciousness are created by brain processes that evolved in natural ways. Although subjective experience is unique in nature, they argue it is not necessarily mysterious. We need not invoke the unknown or unknowable to explain its creation. Feinberg and Mallat flesh out their theory of neurobiological naturalism after John Searle's biological naturalism that recognizes the many features that brains share with other living things, lists the neural features unique to conscious brains, and explains the subjective-objective barrier naturally. They investigate common neural features among diverse groups of animals that have primary consciousness, the type of consciousness that experiences both sensations received from the world and effects such as emotions. They map the evolutionary development of consciousness and find an uninterrupted progression over time without inserting any mysterious forces or exotic physics. Finally, bridging the previously unbridgeable, they show a subjective experience, although different from objective observation, can be naturally explained. And this book is about 122 pages, and the glossary of terms and sources make up the rest, totaling around 200. I might just read a part of chapter 3 entitled Naturalizing Vertebrate Consciousness and Mental Images. As we discussed in chapter 1, according to Nagel, if an animal has something it is like to be, then it has primary consciousness. Some might argue that this is fairly low bar to set for something as complicated and important to human affairs as consciousness. But since we are trying to determine whether an animal has primary consciousness, the most basic form of any experience, then this is a reasonable criterion. We've argued that the brain's construction of mental images and affects is pivotal to the creation of primary consciousness and the explanatory gaps. But to naturalize consciousness, we need to show that these subjective experiences do not somehow magically emerge from the brain out of the blue. To do so, in chapters 3 through 5, we consider which of the living animals have primary consciousness, and we deduce its neurobiological basis, so as to address later in chapter 6 what common biological and neurobiological features make consciousness possible. In this chapter and the next, we focus on the vertebrates, fish, amphibians, reptiles, birds, and mammals, because this is the group to which humans, the only animals known to be conscious with certainty, belong. In this chapter, we ask, which vertebrates have image-based consciousness, mostly of the exteroceptive type, and we can compare the relevant neurobiology across species. In chapter 4, we do the same for affective consciousness, and in chapter 5, we turn our attention to invertebrates. Most people study consciousness have gone beyond the long-held notion that only humans have primary consciousness. Many now assign consciousness to all mammals and birds, both of which have an expanded dorsal pallium of the forebrain. In mammals, this is the cerebral cortex, and the central ideal is that the cerebral cortex and the equivalent bird pallium is responsible for consciousness as it works together with another part of the forebrain called the thalamus. One line of evidence for this idea is that damage to the corticothalamic system in humans leads to loss of conscious sensations and images. This finding offers convincing evidence for the humans and other mammals, but we should also consider the other groups of vertebrate animals whose cerebrum lack a cerebral cortex. Even fish appear conscious because of their elaborate senses, their advanced hierarchical sensory anatomies, including sharp vision, and the alert attention they pay to stimuli. Therefore, since we want to elucidate the most basic neurobiological underpinnings of sensory consciousness, it makes sense to look at the more basal species. Based on our reasoning that any brain that can create mapped sensory images has exteroceptive primary consciousness, we look for the most basal vertebrates that have the neural architecture for isomorphically mapped multi-sensory representations. Somewhat surprisingly, this turns out to be a feature of all vertebrate brains. In mammals and birds, we find the main isomorphic maps in the cerebral cortex. Mammals, with the corresponding in large parts of the cerebrum in birds, though they appear in different cortical locations in these two animal groups. You can see a sort of diagram of mammal brains and birds' brains. And the locations of the regions anatomically indicated here. The optic tectum makes up a relatively large part of the brains of fish and amphibians. We deduced it to be the site of image consciousness in these animals. In all the vertebrates, its map lets the animal tend to look at and turn toward the most important object in the visual field. In fish and amphibians, the tectum is said to be for object recognition and perception. These are terms of consciousness, so our claim for tectum consciousness is not merely based on anatomical mapping. Follows, therefore, that the brain site of image-based consciousness shifted from the tectum of more basal vertebrates to the cerebral cortex during the evolution of mammals. Brain scientists are just starting to study the tectum at the level of its sense-integrating neural circuits, but early findings hit that it is complex enough to form highly processed images for directing behaviors in space. The tectum contains 3 or more layers of densely packed neurons of up to 15 different neuron types. And but along with its many sensory inputs, it has extensive connections to both lower and higher centers of the brain that control actions. However, we are not claiming that the tectum performs all the tasks of image consciousness in fish and amphibians. The tectum does not perform smell perception, as it receives no direct input from the smell pathway. Pallium of the brain's cerebrum performs that function instead. This means smell consciousness has always involved the pallium in the first vertebrates to mammals. Also, the pallium, not the tectum, is the location of the main memory-forming part of the vertebrate brain, named the hippocampus. Using the hippocampus to recall memories is an essential part of consciousness. Remembering and re-experience the look of a previously encountered predator, for example, permit instant recognition and escape. Furthermore, the tectum does not determine the level of consciousness, the amount of arousal that establishes how alert the animal is to stimuli. All vertebrates use the same non-tectile brain regions for arousal, especially the reticular formation in the brainstem and parts of the basal forebrain. Neurons of these regions project widely throughout the brain and release chemicals for arousal, alertness, and vigilance. To summarize, smell, memory, and arousal are parts of consciousness in which the conscious tectum is not primarily involved. The optic tectum does play a role in selective attention, which is a vital function for consciousness. Selective attention is important because we are most conscious of those stimuli to which we attend. As mentioned earlier, the tectum finds out which objects in viewed space are most important or salient, and it directs the eyes to look toward that selected object. For this process, scientists formerly believed that the tectum had to team up with the nearby centers of the brainstem, called the isthmus nuclei. However, a recent study of a basal fish, the lamprey, indicates that the tectum can do it alone in an extremely interesting way. When an object in a lamprey's environment emits two different kinds of sensory signals, visual signals and electric fields, then both these inputs converge on the same neuron at the tectile map, and the neuron signals the eyes to look at the specific point in space from which the two signals arose. The study thus not only showed that the tectum can direct attention by itself, but also emphasized the tectum's role as a brain region where multiple senses come together. Michael L. Woodruff says that the type of attention most likely to reveal a fish has image-based consciousness is persistent visual search for an object in space, such as a food item or mate. He has described a study by Moore Bentov and her colleagues on archerfish who seek to find insect prey in the foliage above their estuary water, then shoot down this prey with jets of water. The link to consciousness is that the archerfish must have a mapped mental image of both the background scene and of the intended prey item against the scene. And Bidentov found that the neurons responsible for this distinction are in the archerfish's optic tectum. This is how Woodruff traces conscious attention to the tectum in a jawed fish. Past work focused heavily on the value of lampreys for revealing the origin of consciousness. Lampreys are a jawless fish and the oldest surviving group of vertebrates. A lamprey has the smallest brain per body size of any vertebrate. Yet it has all the complex sensory organs of vertebrates, from excellent eyes for vision to sensitive touch, keen smell, hearing, and the typical fish sense for detecting electric fields in the water. The lamprey brain has a perfectly respectable optic tectum, with the same type of mapped hierarchical input of multisensory information as in any fish brain. Thus, if fish have image-based consciousness, then lampreys do too. The next big question is, are these tactile sensory representations in lampreys and other fish really conscious? To this we say yes. Just like all sensory images, including those experienced by humans, lampreys' images meet the criteria of the neuro-ontologically subjective features of consciousness we presented in Chapter 2 in Hints of Subjectivity. First, the images are referred to the environment. Put another way, the lamprey responds appropriately to complex visual stimuli in the environment. Second, the images are unified. Lampreys have been called vampire killer eels, and the way they choose, approach, and attach to the swimming fish that they parasitize also suggested size, shape, movement, color, and so on of these environmental targets are bound into unified sensory images in the lamprey brain. Third, these images are causal. By this we mean that a lamprey can respond to environmental stimuli in complex, prolonged, planned, purposeful, non-reflexive ways that cause material changes in the external world via movements. For example, lamprey mating behavior is complex and involves moving rocks to build a nest in the stream bed. Finally, the sensory images are qualitative. By definition, consciousness recognizes different qualia as distinct from one another, and fish can perform high-level sensory discriminations based on sounds, visual characteristics, electrical signals, smell, and taste. Hence, we argue that the sensory images of fish possess all four of the neuro-ontologically subjective features of consciousness we associate with subjectivity, and by these criteria, they are creating conscious mental images. In other words, there is something it is like to be a lamprey. It then follows to echo Nagel's famous question, surely there is something it is like to be a bat. To summarize this section, we began with the basic deduction that mapped multisensory representations in the brain indicate mental images. Then used that deduction to reason that all vertebrates have image-based consciousness. Given this foundation, we can start to look for additional shared features of consciousness by comparing and finding commonalities between the conscious sensory pathways of mammals and lampreys. The shared features we have identified so far include having many complex sensory receptors in eyes, nose, etc., a brain, sensory pathways arranged in hierarchies that are at least 3 neurons long, a place in the brain where multiple senses come together, and brain locations for arousal and directing attention. We identify more such features in upcoming chapters. The invertebrate cousins of vertebrates. From the features we have just deduced, it follows that animals that lack primary consciousness must have less elaborate sense organs and brains and use reflexive behaviors and simple movement programs that do not need a unified image of the world. Let us look at the closest living relative of vertebrates to see whether they qualify as non-conscious or conscious. These relatives, all of which live in the ocean, are the fish-like amphisucks, can't pronounce that word, or cephalochordates, and the bag-like tunicates, or sea squirts. The fossil record shows that they and the vertebrates split into separate lineages before 520 million years ago, during the period of Earth history called the Cambrian. The neurobiologist Thurston Lacali has studied the amphisucks and tunicate nervous systems for decades, and his works provided much of the following information. By our criteria, the nervous systems of these animals lack the complexity required for consciousness. Their sensory equipment is not up to the task. They have simple light receptors, mechanical touch receptors, and possibly chemoreceptors, but not the camera eyes, ears for sound detection, or odor-smelling noses of vertebrates. Tunicate brains, or cerebral ganglia, are small with several hundred neurons at most. The infectious, the sensory pathways to the small brain, although only studied in young larvae, have just one or two levels of sensory neurons that seem to belong to reflex arcs rather than to long hierarchies of information processing. As shown, light detection and mechanical touch are the main senses, and they arouse the animal to swim by signaling a motor center. Researchers have not found a pallium or tectum in these brains. I guess I'll finish up for now, but I only have one chapter left to finally finish this book, and just thought it would be enlightening to read some other material. So, see ya for now.